Good afternoon, everyone. I hope you are doing well. Wait for 2 minutes and then we'll start the class. Okay. Uh, Good afternoon, everyone. I hope all of you joined right. Okay. Then, do you remember what we discussed in the previous class? Hmm? Try to remember. Okay. Uh, no. The thing what we discussed in the previous class was simple. What we have seen different type of equilibriums, right? Where based on phase of the equation. Like in the reaction, there are different types of phases, not more than one type of phase: gas liquid or gas solid or gas liquid solid, all three types. So we call these types of mixed phases as heterogeneous phases. And if there is only one type of phase, only solid or only liquid or only gas throughout the reaction, all the elements, reactions and reactants and products are in same phase, we'll be calling them as homogeneous equilibriums, right? So we have seen that. For today, we will be going to cover. Yesterday we stopped at Gibbs free energy, right? So we are going to relate the Gibbs free energy with equilibrium constant using the mathematical formula, so that we can predict the spontaneity of the reaction. Like based on the K equilibrium value, whether it is 1 or greater than 1 or less than 1, we'll be seeing whether the reaction will happen or the equilibrium will be attained spontaneously or non-spontaneously. Now, after completing this, we'll be seeing how to calculate equilibrium constant through the reaction itself. We have seen how to write the reactions, right? So based on that only, and then we'll be seeing degree of dissociation. Nothing but how many molecules are being dissociated into products, like how much amount of reactant is being decomposed into products. After seeing this, we'll be going to Le Chatelet's principle. Okay, very much important, Le Chatelet's principle. You need to understand it properly. So before going to it, let's have a quick recap. First thing what we discussed yesterday about, let me change the color, homogeneous equilibrium, right? After learning about homogeneous equilibrium, where like what happened, all products and reactants were in same phase. No, after learning about homogeneous, we learned about heterogeneous equilibrium, right? Heterogeneous equilibrium, nothing but we will be having more than one phase. Now, after seeing a homogeneous and heterogeneous equilibrium, we went to equilibrium constant in gaseous phase. That is nothing but Kp. How to write Kp we have seen, right? After seeing Kp, we went to see how to relate Kp and Kc, right? What was the equation we have seen here, where Kp was equal to Kc into RT power delta. This is what we have seen, right? Yes or no? No. If you remember properly, what was delta N? Delta N was nothing but number of moles of products, that too in gas phase, minus number of reactants in gas phase again. Simple. That was delta M. So using how many products are in gaseous phase and how many products are in how many reactants are in gaseous phase, we related Kp value, that is equilibrium constant in terms of pressure, to Kc value, that is equilibrium constant in terms of concentration. How we related with this? By using ideal gas equation, that is PV is equal to nRT, where we have written P is equal to N by VRT, where N by V is nothing but our concentration. Just in case of pressure term, we are keeping Kp. In presence of concentration term, we are keeping Kc into RT power delta N. You want to go through the derivation, how we did that. Try to Go through your notes once again. No, this is what we learned yesterday, and at last we ended up with the Gibbs free energy equation where we know that delta G is equal to delta H minus T delta S. Now, after seeing this, we came to a new mathematical equation where delta G is equal to delta G naught plus RT ln Q. Q is nothing but our reaction coefficient, right? We learned, right, what happens to the reaction coefficient if it is greater than K equilibrium, or if it is less than K equilibrium, what will happen? No. If let's say reaction coefficient is less than K equilibrium, then what happens? The reaction will go to forward so that it will attain the equilibrium. No. If Q reaction coefficient is greater than K equilibrium, then the reaction will go backward. Simple, right? We have seen these things, right, yesterday. So today what we are going to learn, first thing we'll be doing some problems based on the equilibrium itself first, and then we'll go to Gibbs free energy equilibrium relation concept. Now this was the homework. All of you completed it or not? Try to answer in the chat. Okay. Okay, fine. Okay, good. Simple, right? All of you got the answers, right? So let's verify your answers now. Now, what we need to do, nothing but Kp is equal to Kc into RT power delta N. Just find delta N values for everything. Now, first reaction A, we are saying delta N is equal to how many moles of gaseous products are there? 2 moles minus how many moles of gaseous reactants are there? 4 moles. That is nothing but minus 2 is our power here, where Kp is equal to Kc into RT power minus 2. Okay, simple. Now, if you want to relate the Kp Kc value here, first find out delta N, that is equal to how many gaseous products are there? 2. How many gaseous reactants are there? 1. That is equal to minus 1. Now, here Kp is equal to how much? Kp is equal to Kc into RT power minus 1. Simple. Just find out the delta N value and you can substitute there in the formula. You'll get the Kp and Kc relation. Simple, right? Nothing complicated here. Now, let's continue to our today's class, that is a mathematical expression for thermodynamics is already given here. That is delta G is equal to delta G naught plus RT ln Q. What is Q here? Q is nothing but our reaction coefficient. Okay. What is delta G naught? What is delta G naught? Delta G naught is standard free energy or standard Gibbs free energy, we can say. What is delta G? Nothing but it is a Gibbs free energy, not a okay. No. Standard free energy change is the free energy change for a process at 298 Kelvin and 1 atmosphere pressure, in which the reactants are in standard state are converted to products in standard state. What we need to see is first thing, pressure and temperature should be constant. If we learn this in thermodynamics, right? That too exactly. If you want to call it as a, if the energy term should be a standard term, then you need to do the experiment according to the standard conditions, that is 298 Kelvin and 1 atmosphere pressure. And we need to see that the reactants are from standard state. Let's say you take carbon. Now, what is the standard form of carbon? Nothing but solid, right? Graphite is the most stable form. So the stablest molecule you take of that particular compound, and you need to start the reaction from the standard state, stable one. Okay. If you are converting into products, let's say chlorine is converted, so you write chlorine as gas because it generally exists as gas at standard conditions, that is 298 Kelvin and 1 atmosphere pressure. That's what you need to see here. Okay. Now, if we know at equilibrium, we learned this in thermodynamics, right, where delta G will be equal to 0 at equilibrium. Why? Because how much forward reaction is happening, the same amount of backward reaction is also happening. So what happens? Delta G will be equal to 0. Then what will the equation will be? 0 is equal to delta G naught plus RT ln Q. Now, at equilibrium, Q is equal to K equilibrium, right? Yes or no? So now substitute the values here. where delta G naught is equal to minus RT ln K equilibrium. Simple, right? Now, using this formula, we'll be seeing whether the reaction is spontaneous or non-spontaneous, or the reaction is not happening at all. That is, the rate of forward reaction is equal to rate of backward reaction at equilibrium state or not. We'll be seeing this. No. If you see here, I think you can see, right? Now, if you see delta G naught is equal to minus RT ln K equilibrium. Now, if you elaborate that, delta G naught is equal to minus 2.303. This is 303 minus 2.303 RT log K equilibrium, right? Now, if you see that K equilibrium is greater than 1, then nothing but what you need to see, log value. Let's say K equilibrium is 1 now. Initially take K equilibrium is 1. Now, what will the delta G naught value will be? If log 1 is nothing but 0, what will delta G naught will be equal to? 0 itself, right? So, in that way, you are going to compare whether if it is greater than 1, what is the value for G naught? If less than 1, what is the value for G naught? And if it is 0, if it is 1, what is the value for delta G naught? That's we need to see. Okay. Now, in the first case, what I am taking, K equilibrium is greater than 1. Then what happens? Log is greater than 1. What is greater than 1, you will get a negative value again, right? So what delta G naught will be? Delta G naught will be negative value itself, right? So if it is greater than 1, you'll get a positive value only. So if you are multiplying delta G naught is equal to minus value is there. Now log K equilibrium is positive value. There you'll get as negative itself, right? Now at that time, what will it say? If delta G naught is negative, the reaction is spontaneous. Okay. The reaction is spontaneous and the reaction is forward direction. How did you say this? You know, right? What is K equilibrium? Nothing but concentration of product by concentration of reactant. If you want to say that the K equilibrium value is greater than 1, that means the product concentration should be high, right? If you want to keep the product concentration high, the numerator high, what should happen? Forward reaction should happen more when compared to backward reaction, right? Simple. Just apply the concept. Now, next one, where K equilibrium is less than 1, where log K equilibrium value, if you are taking less than 1, that means you'll get a negative value. If you take in that case where delta G naught is equal to negative value into negative value, that gives you a positive value for G naught. If delta G is positive, that means it is a non-spontaneous reaction, okay? If delta G is positive, that is a non-spontaneous reaction, endergonic reaction. Now, if that's the case, then what is the reaction? If you want to keep K equilibrium less than 1, that means reactant concentration should be more. That is, backward reaction should happen more. So in that way, we'll be taking reaction is in backward direction. Simple, right? Now, if K equilibrium is equal to 1, that is product concentration as well as reactant concentration is equal. Exactly 50%, 50% is there. Now, then what we'll be saying, delta G naught also will be equal to where log 1 is 0, right? So that's why. And we'll be saying delta G naught is also equal to 0. So equilibrium is there. So we cannot say whether the reaction is spontaneous or non-spontaneous. Now the shift in reaction will not be in any direction. Whether the forward reaction not be more when compared to backward reaction, or backward reaction will not be more when compared to forward reaction. So everything will be equal there, the forward and backward reaction. So there will be no shift in any direction there. Okay. If you have any doubts, try to mention it in the chat. Okay, if you don't have any doubts, then let's move to the next concept. Main thing, try to go through this point wise. Okay, I'll give you step-wise analysis here. First thing, how to calculate equilibrium concentrations. That is how to write the concentration terms or the pressure terms. And then we'll be seeing how to calculate the equilibrium constant or pressure constant, equilibrium pressure constant. First thing, the concentration of various reactants and products can be calculated using equilibrium constant and the initial concentrations. Okay, using equilibrium constant and the initial concentrations. For calculating equilibrium concentration, we need to follow certain steps. Try to go through this. Okay, you'll be seeing only 4 steps. Okay, follow these 4 steps, you'll get the answer exactly proper. Don't get confused how to write this. Okay. This already we discussed. Just I'm repeating it one by one again so that it will be more clear for you. Now, let's take a question here. That is 1 mole of N2 is taken. Okay. Moles of N2 is equal to 1 mole. And then 3 moles of H2 is given. Number of moles of H2 is equal to 3 moles. Now, volume of the vessel is given, that is 1 liter. Okay. Find the concentration of NH3 at equilibrium. First, write on the balanced equation itself, right? What we need to write? Already moles are given, 1 NH2 plus 3 H2 gives rise to, or in equilibrium with, how many moles of ammonia? Just balance the equation, where 2 NH3. Okay, all are gases itself, right? He also gave that equilibrium pressure, that is final pressure is 1 atmosphere, and the equilibrium constant at 400 Kelvin is Kp is given, that is 4 by 27. Okay, temperature is given, that is 400 Kelvin. Now these are what already mentioned here. So by using this data, we need to find out the equilibrium concentration of ammonia. Okay, equilibrium concentration of ammonia we need to find. How to find that? Okay, first what you need to do, write the initial concentrations. What did I say? We need to take the active masses, right? So all our gases, so we need to calculate all the active masses as moles and volume is given. Try to calculate the concentration term itself. Now initial moles is 1, and what is the volume taken here? 1 liter itself. Initial moles is 3, volume taken is 1. What is the initial moles of ammonia formed? Can you answer in chat? Initial moles of ammonia formed is 0, because at the start of the reaction there is no ammonia, right? Now, let's say after some time, that is, let's say the reaction reached equilibrium. Then what is the concentration of ammonia? Nothing but 2 moles of X. Now, let's say you have 1 mole of something and it gave a product of 0.5 moles. Okay. Now, how much of the initial reactant is lost? How much of the initial reactant is lost? 0.5, right? 1 minus 0.5. So the same thing, let's say if you are having a reactant and is give rise to 2 moles of product. Now it is 1 mole is there, it gave rise to, now 1 mole is giving rise to 2 moles, right? Let's say 0.5 is coming out decomposing. Now 0.5 gives you twice, that is 2 into 0.5, that is nothing but 1 mole. Try to be clear with this, okay? If 1 mole gives 1 mole, that means if 0.5 moles is given, that means exactly 0.5 moles of reactant is decomposed. Now if 1 mole is giving 2 moles, that is if 0.5 moles of the reactant is decomposing, exactly twice of the 0.5 moles of product will be produced. Try to keep this in mind, okay? Now using this concept, as there are 3 moles are giving 2 moles, that means 3 moles are decomposing to give rise to 2 moles, right? 3 minus 3x, simple. 1 minus x for nitrogen, and as 3 moles of hydrogen we are using, we are keeping it as 3 minus 3x, and for ammonia as 2 moles are produced, that is 2x. Simple, right? Now, after writing this, you need to write the Kp value now. Kp is equal to, as the concentration terms are same here and volume is also same, directly you can multiply with the Kp value. Nothing but concentration of NH3 power 2 products, right? Then divide by reactants concentration. That is concentration of N2 into concentration of H2 whole power 3. Simple. This is what the reaction is. Now substitute the values here. Now step 3, what we need to do? Substitute the equilibrium concentration in the equilibrium equation. Okay. Now whatever we deduced, all those things you need to substitute here. Okay. Like the equilibrium concentrations, just substitute them in the equation now. Now, if you substitute, what you'll get? 2x square, right? By 1 minus x into 3 minus x cube. Now, if you just try to elaborate this one, okay, where kc is equal to 4x square by 1 minus x into 3 of, I'm taking 3 common, I'm writing it as 1 minus x whole cube. 3 cube into 1 minus x whole cube. Now this is exactly nothing but 4x cube x square by 27 into 1 minus x whole power 4. Okay. Now, Kc value is already given, right? Kp value is already given. What is Kp value given as? Equilibrium constant is given. Okay. Equilibrium constant is given as K equilibrium is given as 4 by 27. Directly substitute the value of 4 by 27 here. 4 by 27. If you see this, just try to convert this. Nothing but 27, 27 cancel and 4, 4 cancel. What this is equal to? This is equal to 1 is equal to x square by 1 minus x whole power 4. Now convert this into a quadratic equation. Got x square by 1 minus x whole power 4 is equal to 1. Now convert this into a quadratic equation. Okay. First thing what I did, I just sent the other side, right? No, next what I did, just I send this whole square to the other side. What I did, I written this one as x by 1 minus x whole square, again whole square, right? The power is same, is equal to 1. Send the square to the other side where you will be given this, where x by 1 minus x whole square is equal to 1 again. Simple, right? Now after doing this, we give the quadratic equation where x square minus 3x plus 1 is equal to 0. After writing this quadratic equation, try to use the formula, right? Remember the formula? Nothing but minus b plus or minus root 4ac by 2a, right? Using this formula, what we did, we use this quadratic equation, find out the value of x. So we'll get two different values, right? One is plus value and one is minus value. Try to do that. Now, if you substitute, that is nothing but 3 plus or minus under root 9 minus 4 by 2. Then what we'll get, if you are taking the plus value, that is root 5. 3 plus root 5 by 2, that gives us 3 plus 2.24 by 2. Now, the value will be around 2.62 value. Okay. X will be around 2.62 by using the plus value. Now, let's use the minus value here. If you use the minus value now, 3 minus root 5, what you'll get, X will be around 0.38. Okay. So, if you see in both the cases, you know what is the initial concentration of nitrogen? X is equal to 1. No, if can the product be more than 1? No, right. The product cannot be more than 1. So here we'll be neglecting the x is equal to 2.62. So we'll be going with x equal to 0.38, as the amount of product cannot be more than amount of reactant. If 1 mole of reactant is there, I can get only 1 mole of product only, right? If 1 mole of reactant is there in equilibrium equation, that is giving 1 mole of product. Can I say 1 mole of product reactant is giving 5 moles of product? No. In a balanced equation, if the 1 mole of reactant is giving rise to 2 moles of products, that is fine. But in a balanced equation where we use nitrogen, which is giving only 1 mole of product, so we cannot say that it can be more than 2. Okay, it cannot be more than. No, if we go through this where x is equal to 0.38, using this value, just substitute the x value for concentration of, what is concentration of NH3 is equal to, how much concentration is there? 2 moles of NH3 is there in the solution. That is nothing but 2x, where 2x is equal to 2 into 0.38, right? Now, what is the value? If you find that out, 0.76 is the concentration of mole per liter. This is the concentration of ammonia. Okay. If you ask anything more, you can substitute the values here, x value here, and you'll get the concentration of each and everything at equilibrium. Okay. Simple. If you ask the equilibrium constant also, you can directly substitute all the values, you'll get the equilibrium constant back again. Now, are you clear with this concept? If you are clear, we'll be going to next concept, how to predict the extent of reaction. Whether the reaction is going more forward direction or whether the reaction is going more backward direction. If you are clear, try. If you are not clear, try to mention your doubts here. Okay. Huh. See here, why we are not considering x is equal to 2.62 is what happened in the equilibrium reaction. Try to remove the value. Now we know that 1 mole of ammonia is producing 2 moles, right? Now if the e- x value is more than 1 or 2, what happens? The concentration of ammonia will be greater than the concentration of nitrogen, where nitrogen not even available that much, so it cannot produce the ammonia, right? That much ammonia. So if 1 mole of ammonia is producing, simple terms we can understand. See, if 1 mole of ammonia is giving 2 moles of, if 1 mole of nitrogen is giving 2 moles of ammonia. Okay, 2 moles of ammonia is given. Now, if already we are saying that 4 moles of ammonia is given from 1 moles, then is it correct? It is wrong, right? So that's why we are neglecting the x is equal to 2 point there. Okay, if x is equal to 2 already, then 2 into 2 4. Can nitrogen give 1 mole of nitrogen give 4 moles of ammonia? No, it cannot give. In the balanced equation, we know that 1 mole of nitrogen gas can give only 2 moles of ammonia. Okay, try to keep that in mind. Which one you need to consider and which one you not to consider. Just try to see what is the uh, relation in the balanced equation, and based on that you can see whether you can take the x value as that one or not. Okay, is your doubt clear? Okay. Ah, if are you clear, then we'll go to next concept, that is predicting the extent of reaction. What you are seeing here, nothing but K equilibrium is nothing but what? Concentration of product by concentration of reactant. If K equilibrium is equal to 1, that is exactly how much forward reaction is happening. Same amount of backward reaction is also happening. Let's say K equilibrium is equal to 10 power 3. What does that mean? That means the product concentration is more. If you want to keep the product concentration more, then more reaction should happen or more backward reaction should happen. Yeah, if you want to keep the forward reaction more, if you want to keep the concentration high, forward reaction will be more than the backward reaction rate. Simple. If you want to keep K equilibrium as 10 power minus 3, nothing but reactant concentration is more here. If you want to keep the reactant concentration more, that means backward reaction should happen more. Right? Simple. No. If we write it properly, in case 1, nothing but K equilibrium is greater than 1. In case 2, where K equilibrium is less than, or let's say it is less than 10 power minus 3. Now, in this case where 10 power 3 K equilibrium is greater than 10 power 3, in this case what happens? Product concentration is more than concentration of the reactant. If you want to keep concentration of product more, that means forward reaction is happening more. In this case, the reaction is product favorable. Now, if K equilibrium is less than 10 power minus 3, that means reactant concentration is very much high. The only thing is backward reaction is more favorable, or reactant is more favorable rather than product. Okay. Now, if you understood the concept, just try to go through this question. I'll give you 1 minute. In which of the following does the reaction go almost to completion? Just try to compare the previous concept and say in which one where the product will be going to. I'm not saying completed. I'm saying going to completion. Yeah. You are right. Right. Directly you can see if 10 power minus 2 or 10 power minus 3 is there, that means it is reactant favorable, right? That means it is going backward reaction. It is not going to completion, right? Now, if you see in A, B options, that is 10 power 3 and 10 power 2. In both cases, which one is going to be almost completion when comparatively? 10 power 3, right? Simple. That's it, 10 power 3. The answer will be option A, where Kc is equal to 10 power 3, where the product is more favorable. And 10 power 2 also product is favorable, but comparatively, if you see, A will be having more product concentration rather than B. Now, our next concept, that is degree of dissociation. 1 second. Let's continue. Now, first thing, what is degree of dissociation? Nothing but he is asking. Let's say you have 10 grains of, let's say you have one chapati and you are tearing it into exactly half. Now, how much time you are taking, or let's say what is the final number of chapatis you have, or final part of the chapati you have, and what is the initial part of the chapati? That is nothing but degree of dissociation. How much it is going undergoing dissociation, right? From compared to initial state. How many dissociations are undergoing? That is nothing but degree of dissociation. Simple. No, it is a fraction of 1 mole. Generally, we'll be seeing for 1 mole itself. 1 mole dissociated into its product. Let's say 1 mole is dissociating into zero point 0.5. Then nothing but what happened? Exactly half mole it is dissociated. Then what we'll write? Alpha is equal to how many moles dissociated by initial value. Now, what is the alpha value? That is nothing but 0.5. Simple, right? Now, if they ask percentage degree of dissociation, what you need to do? Just multiply alpha with percentage degree of dissociation. Just multiply alpha with 100. That is nothing but 0.5 into 100. That gives you 50% dissociation. That is reactant. If you are taking 20 moles of reactant, exactly 50% of 20 moles will be reacting. That is 10 moles will be reacting and 10 moles will be the same as reactant itself. If alpha is 100, if alpha is equal to 1, what does that mean? Whatever reactant you are taking, all the reactant is completely converted into product. That is the alpha value. That will give you how much amount of the reactant will react, or how much amount of the reactant will decompose or will convert into product. This is what we'll be knowing using degree of dissociation value. Generally, we'll be defining this for 1 mole, and then whatever moles are given, we'll be calculating for that. Okay. So if alpha value is given, that is for 1 mole itself. You can write down this one, that alpha is nothing but number of moles dissociated by initial number of moles taken. Okay. Now, what is alpha? Alpha is nothing but fraction of moles dissociated out of fraction of moles dissociated out of 1 mole. Okay. That is nothing but alpha. Simple. Remember, what do you calculate? Degree of dissociation is for 1 mole of the compound itself. And by knowing alpha, we can say if you take n number of moles also, you can say how many moles of the compound will be reacting or not. If they ask you percentage dissociation, directly multiply alpha with 100. Simple. Now, let's say we have 5 moles of PCl5 is taken and 2 moles of PCl5 dissociated. Then what is the degree of dissociation for PCl5? What is the alpha value for PCl5? Try to calculate now. I'll give you 1 minute. Calculate. You have 1 minute, and then I'll discuss the answer. No, this is simple answer, right? What you need to do? Nothing but how many moles dissociated? How many moles dissociated? 2 moles. You know that, right? Now, if 2 moles is dissociated, and what is the initial number of moles? That is 5. Nothing but 5 by 2 by 5. What is the value? Nothing but 0.4. If they ask you percentage degree of dissociation, Percentage DOD, let's say, that will be 0.4 into 100. What is the degree of dissociation? Percentage degree of dissociation, that is 40%. You take 5 moles, exactly 40% of 5 moles will be dissociated. Or if you take 100 moles, exactly 40%, and that is nothing but 40 moles will be dissociated. Simple. Now, again, let's assume AN is a compound, okay? Atomicity is N. AN is there. It is completely dissociating to N moles of single atom, that is A. N moles of A. Now tell me, what is the alpha value here? Now tell me what is the alpha value here? Now, in these cases, same thing again, what you need to take. How many moles of A is formed from how many moles of initial reactant? So before that, by using alpha value, what we can do? By using alpha value, can you find out a K equilibrium or not? Yeah, we can write. You know the degree of dissociation, right? How much amount of the reactant is reacting, you know. So by that, by using this formula, we can again calculate the K equilibrium and all also. So let's see how what in what case we'll be using alpha value and how to calculate the concentration, equilibrium concentration of the reactant or equilibrium concentration of the product. How to do it? First, write on initial conditions. Initial conditions. What is the initial conditions? Let's say concentration of AN is A. Okay, and concentration of n moles of A product is 0, right? Initially. Now at equilibrium, what is the concentration of AN? Nothing but n moles of X will be formed and A minus X is lost. If X moles of A is lost, exactly NX moles of A will be produced. Same, right? If 1 mole is lost, N moles is produced. Same thing, if X moles is lost, NX moles will be produced. By using this, will be doing. Hmm. Let's say you know the concentration, and then you know alpha is what? Nothing but how much moles of the compound is dissociated. Nothing but how many moles of product is formed. Exactly, right? Now, if you write like that, X, you can write it as X moles. Let's say for initial, we are taking X by initial value of the reactant is A. That is nothing but X by A. Now, if you want to know X is equal to alpha, substitute the alpha X value as alpha A now. Substitute this in the equation where you can write it as A minus A alpha into Na alpha. Simple. X I am substituting as A alpha. Simple. Okay. Now you know these are the total moles at equilibrium, right? Total number of moles at equilibrium. These are the total number of moles present at equilibrium, right? What is the concentration or number of moles of A present? Nothing but A minus A alpha. And what is the constant number of moles of product present? That is Na alpha. Nothing but you can write as A minus A alpha into or plus into Na alpha. Simple, right? Now, what you can write it as? You can take alpha common and or A common, and you can write the whole equation, rewrite the whole equation, right? Now, if you want to write it in that way, nothing but you can write as first, let's say A minus A alpha plus Na alpha is there. Now, let's take alpha common from this. What you can write this as? I'll go to next one. This is equal to A minus A alpha plus Na alpha, right? Now, take alpha common first thing. If you take alpha common, you can write it as Na minus A into alpha. Now take A common itself, A common. Then you can write as 1 plus n minus 1 into alpha. We taken A common, right? This is nothing but A value. So if you know the initial concentration of the reactant, how much amount of reactant you are taking, and what is the moles of the product formed from the reactant, and what is the dissociation constant or degree of dissociation, if you know, then you can directly find out the total moles of the reaction, total number of moles of the reaction. Simple, right? Now, what is N here? N is nothing but we can write as sum of number of moles of products by sum of number of moles of reactants. Simple. This is nothing but N value. You can find out using this formula, or you can find out using by writing the equation also. That is fine. By using this, we'll be substituting the N value, and then we'll be getting the total number of moles value. Okay. Sit. So this is how we find out alpha, or we use alpha to find out the total number of moles of the reactants as well as products combined in the reaction. By using this, we'll be seeing how to find out if you know the reactant concentration and if you know the total number of moles in the reactant, then indirectly you can find out that moles of reactant present at last or moles of product formed at last. Simple. Now, using the same concept, write the equation for this one also. Calculate Kp value here by using this formulas. First thing, initial where time is equal to 0, concentration of PCl5 is A, other products is 0. Now at equilibrium A minus X is there, and X moles of PCl3 is formed and X moles of Cl2 is formed. Now if you don't know the moles, nothing but A moles, let's say AX moles will be forming, let's say. No, if AX moles of X is formed, in N moles you are taking like that, A moles I am taking. So if you are taking A moles, if you're taking A moles, then we'll be writing it as A minus AX and AX. Simple, right? Now, if I want to write the total moles is equal to what? A minus AX plus AX plus AX, right? Now, this is equal to what? A plus AX. Simple. Total moles is equal to how much? Total N is equal to A plus AX. Simple, right? Now, using this, we'll be writing the pressure constant. Now, before writing to Kp, what are these values? These are moles, right? So, convert this in terms of pressure. If you want to convert this into terms of pressure, if you remember Dalton's law of partial pressure from states of matter, what does it state? Nothing but partial pressure of any gas, let's say Pa gas is there, nothing but mole fraction of the gas into total pressure. This gives you the value, right? So using this value, we'll be going to find out the pressure of each gas. If you want to write the pressure of, 1 second, let's use our next slide. Okay. Just remember first thing, partial pressure of PCl5. Partial pressure of PCl5 is equal to nothing but mole fraction of PCl5 into total pressure, let it be P. Now, if you want to write partial pressure of PCl3, nothing but mole fraction of PCl3 into total pressure. Now, if you want to write partial pressure of Cl2 gas, nothing but mole fraction of Cl2 into pressure of total pressure. This we have seen. Now, after using these things, just directly substitute them in the value, where mole fraction of PCl5 is equal to, what is the mole fraction? If you see, this is the moles of PCl5 present. What is the total moles? A plus AX, right? Directly substitute this value here. A minus AX by A plus AX. Simple. Now we can cancel out the A values here. We can write it as 1 minus x by 1 plus x. Mole fraction of PCl3 is equal to AX by A plus x total moles, right? Nothing but x by 1 plus x. Right, mole fraction of Cl2 gas, that will be equal to AX by A plus AX. That gives you x by 1 plus x. Simple. Just substituting the total moles present at the equilibrium. Okay. What are the moles of the initial gas at equilibrium by total moles of the gas at equilibrium? Simple. Now, after substituting, now substitute these values total in Kp. Kp is nothing but partial pressure of Cl2 products, right? Partial pressure of PCl3 by partial pressure of PCl5. Now, substitute these values here. Substitute these partial pressures values here, and also as well as mole fraction values also you need to substitute. Now, if you substitute it in that way, for mole fraction of Cl2 is x by 1 plus x by 1 plus x into total pressure. No. Next thing again for PCl3 also x by 1 plus x is a mole fraction into total pressure by what is the mole fraction for PCl5? Nothing but 1 minus x by 1 plus x into total pressure, right? Now, if you see one pressure term, one total pressure term cancel, and 1 plus x cancelled, and 1 plus s cancelled. So, what you will be remaining with? What you will be remaining with here? Now, Kp will be equal to alpha p, alpha square p by 1 plus alpha. 1 plus alpha is left, right? 1 minus alpha. This is what we are left with. Now, if we solve this completely, we'll get alpha square p by 1 plus alpha into 1 minus alpha. If you solve this, we'll get as alpha square p by 1 minus alpha square. Right? Just multiply 1 into 1, 1 into alpha, everything, right? A minus b into a plus b. That one you need to do. No. If you do this completely, we'll get Kp value is equal to 1 minus alpha. Sorry. Yeah. Kp value is equal to what? Alpha square p by 1 minus alpha square. By using dissociation constant and what is the total pressure of the reaction? What is P? P is nothing but pressure at equilibrium. Pressure at equilibrium. Okay. That is the P value. Even if you know degree of dissociation and total pressure at you'll be getting the pressure constant, equilibrium constant in terms of pressure. If you know concentration, you can go with that also. Again, if you know total moles and everything, just try to find out the mole fractions and all. We'll get the total moles. Then you can find out Kc value also. If you know Kp value, you can directly convert into Kc also. That's what Kp is equal to Kc into RT power delta. Simple, right? Now, if you understood the concept, try to apply it for this question. Now, let me do this, no issues. At some temperature, what is given? N2O4 is given, is dissociating into 2NO2. Now, if this is happening at, let's say he's saying that 40% and 50% at the total pressure P1 and P2. At total pressure P1, the dissociation is 40%. That means exactly 1 mole is dissociated into 0.4, right? 1 minus 0.4, and what is the formation? 2 into 0.4, right? Now, at total pressure P2, 50% is decomposing. That is 1 minus 0.5, right? Yes, you need to take alpha, right? Don't forget that. No, exactly 0.5 is formed, lost. That means 2 into 0.5 moles will be formed. If you write these values properly, this will be equal to 0.6, and this will be equal to 0.8. This will be equal to 0.5, and this will be equal to 1.0, let's say. Now, what is the total pressure equal to? P1 is equal to 0.6 plus 0.8, right? Yes or no? Simple. Just combine both the moles present at last. Sorry. Okay. These are moles, right? You cannot write as P1 is equal to 0.8 plus 0.6. Okay. You can write mole fractions there. Okay. 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 Now, if you see this, how to do this problem? Now, you know pressure total is equal to, sorry, total pressure, that is 0.6 plus 0.8, that is equal to 1.4 atmospheres, and the pressure total for, let's say, P1 itself. Now here P2 is equal to 0.5 is the pressure of N2O4, and 1 is the pressure of NO2, that is nothing but 1.5 atmospheres. Clear, everyone? These are pressure itself, sorry. Okay. Now, if you know equilibrium constants doesn't change, right? Even at the P1 or P2, the equilibrium constant will be same itself. That doesn't change. So if you know that, nothing but you can write as Kp1 is equal to Kp2. Just substitute the pressure values here simply. You know the moles, just write the mole values into P1 and mole values into P2. Kp1 you can write, right? What is Kp1? Nothing but mole fraction of NO2 whole square. If you know mole fraction, that is zero point 0.8 moles is there. 0.8 by mole fraction 1.4. Sorry, this is total number of moles, not pressure. Total moles, okay. 1.4 moles and 1.5 moles. If you see here, 1.4 into P1 whole square, total pressure is P1. This is nothing but Kp1 divided by Kp2. That is nothing but, write Kp1 completely first. Kp1 is equal to nothing but 0.6 by 1.4 into P1. This is the reactant term for N2O4. Now, write for Kp2 also. Kp2 is equal to how much? Mole fraction is given as 1 by 1.5. This is for the product, right? P2 whole square, 2 moles of N2O5 is formed by, what is the reactant concentration? 0.5 mole is dissociated by, what is the total moles? 1.5 into P2. If you see P2 and 1 P2 is cancelled, 1.5 is cancelled. Now, if you see all this, if you want to write Kp1 by Kp2, Kp is equal to Kp1, Kp1 is equal to Kp2, sorry. Now, if you substitute this, nothing but zero point 0.8 whole square into P1 by 1.4 into 0.6, that is equal to, what is left here? 1.5, 1.5 is left. So if you write here, you can write as P2 square by 1.5 into 0.5. Right, simple. Just substitute this value here. P2 by 1.5 into 0.5. If you want, what do you want here? P1 by P2, right? Just rearrange the values. 1.5 into 0.5. So this will be in the denominator. Okay. Now P1 by P2, if you want, right? 1.4 into 0.6 by, just this value will be here. 0.8 square into 1.5 into 0.5. If you calculate this value, you'll get the ratio of P1 by P2. Now, this will be around 7 by 4. Around 7 by 4. Are you clear with this answer? If you have any doubts, try to mention in the chat. If you have any doubts, try to mention in the chat. Just first find out the number of moles and then find out the Kp1, Kp2. And then you know that equilibrium constant doesn't change. Equilibrium constants will be same. The ratio will be same. So you can write as Kp1 is equal to Kp2. By using this, we'll be getting the P1 by P2 total pressures ratio. Ratio of P1 by P2. That is nothing but 7 by 4. Okay. So for today, we'll be closing here. And tomorrow we'll be discussing Le Chatelier's principle. Very much important. Okay. Tomorrow we'll be discussing Le Chatelier's principle. So here what we'll be seeing is like if you change the pressure or something, equilibrium constant doesn't change, but the reaction will be affected. Whether the forward reaction is going on or whether the backward reaction is favorable. So we'll be seeing what will happen whenever the reaction is having some kind of external changes to the reaction system. Pressure change, maybe volume change. These kind of changes will happen. So what happens to the particular system, whether the reaction will go forward direction or whether the reaction will go backward direction. We'll be seeing this. Okay. If you have any doubts, try to mention in the chat or you can leave the class.